one of our great colleagues here in the Institute, Professor John Baras. I'm just going to read a bio, which is, of course, very dense, but I'll have to go through it anyway. That's okay. John received his bachelor's in electrical engineering from National Technical University in Athens, in Greece, in 1970, and then his master's and PhD from Harvard in 1971 and 1973. He's been here since 1973 on our faculty in electrical and computer engineering department, and initially he was with applied mathematics as well. John is the founding director of this institute. In fact, the reason we are here today is because of what he did in 1984. And today he's going to talk about his work in model-based systems engineering and tell us about all the great things that he's doing. So, without further ado, John.
Thank you very much. You know you are proud with the introduction longer than the talk. That's not my comment. That's the comment Eric Bloch will remember when you did it after 10 years. And I made very long introduction. Okay, so I'll try to talk to you about component-based architectures for system synthesis. This will be my flag to try to proceed as many things to try to join us. So it just shows you that this issue of complexity is very important to many of the problems that we work with. So what makes it particularly important is difficult is that we have systems that are very heterogeneous in terms of their physics, chemistry, and mathematics. And people talk about system of systems. This is another hot topic. And as I have said to this audience many times before, I strongly believe this is the edge that's going to see who knows what is doing, who are the leaders, and who are not the leaders. Okay? So many of us here do sense, decide, actuate systems, whether we are in microelectronics or in controls or in applications. We have to deal with systems which have multiple scales. And the thing that makes it possible, the talk I'm about to give, is that in information technology, we have a lot of advances that they appear either software or hardware in the systems, and they allow us to talk about systems. So, I don't think this thing is say here. Yeah. Okay. So, so what's happening with information technology is we have these little gadgets which are computers of different kinds now that they're called embedded systems. You know? Can you hear me now?
There's a power button on the top of the box.
Where? Microphone is on. One of them is how to link the cyber side with the physical side. And for instance, although I will not talk about it, we have projects with General Motors about cars. We are looking at the energy efficient buildings and so on and so forth. So typically and abstractly speaking, these things have a physical layer and they have a logical layer. And the physical layer where you do your physics, your chemistry, the kinematics, the mechanics, whatever, and here is the computer side. And there are some examples here from the internet to networks that they come from robotics and so on. So this is another slide. So this is from the project we have on CPS with the Vanderbilt and Notre Dame, where you can see that there are many layers here, starting from humans, going down to hardware and up. And there are many applications of these things in transportation, infrastructure, and so on. So there are a lot of serious challenges here, and the most important one, and we are, according to NSF, the only project that is addressing it, the systems, serious systems integration of these kind of systems, and the challenges are in modeling, constraining, and composing. Right. So we'll talk about it. So let's talk about model-based system engineering. What is that? Many of you know what VLSI is, right? Very large scale integration. So what was the big success of VLSI? Why it changed the world? Because for the first time, it separated the people that they designed the chips from those that they manufactured. You would write the program, and you were the designer, Nobody could stop you. Before they could stop you because you didn't have the factory to manufacture. Now you can send it to the foundry and you get a chip. It's completely changed the market and everything else. And what it did is actually allowed us to do what's called design by compilation. You write a program, it has the appropriate logic, put it in the right chemistry, and an artifact comes on the other side. So if I don't leave you with anything else from this talk, is one of the things that model-based system engineering is trying to do is similar kinds of advances when the physics of the system are not just silicon, but mechanics, cars, any kind of system. So one of the dreams is we want to make design and compilation process. So why is that different? Because you have to do several things, including system behavior, which is the dynamics of the system, which most of us do. But where we don't pay attention is on the system architecture of the structure and the mapping of dynamics on structure. So we're going to talk about that. Even control people paid attention to the behavior, to the relationship between behavior and structure in the very early days of control, and they forgot about it. So what's the best analogy of this? You are trying to run a distributed program, which is the behavior. A program in the sense of computer programming. And you try to run it on a multiple chip platform, which is the behavior. That's the architecture, which tries to answer the question of what the system consists of. And your problem is to understand how you map the program into the distributed architecture. This is a computer engineering problem. And so things like that are called the platform-based design by people like Professor Alberto Sangiovanni of Berkeley and many others. I prefer to call them model-based system engineering, and there's a debate about which term is the better, but it doesn't matter. What matters is what is the substance. Okay. And things in system engineering are several inspirations have come from software engineering because, what did we do in software engineering? We wrote programs at the beginning, we lower level languages, and we went up to C, and then we went to C++ because of object-oriented programming. We would like to have boxes or programs and then let them communicate all this as boxes. And then we went to something that's called component-based software. And now we're talking about component-based system engineering. This is much harder because the constraints in software are, in my opinion, much simpler because you have to worry only about the structure of the language and the constraints of the language. Here, in system engineering, you have to worry about the constraints that come from the logic of the physics and the various things, right? So, for instance, in VLSI, it wasn't for Lynn and Conway that they actually understood the design logic that we need and the design rules for silicon. We wouldn't have compilation, design by compilation of VLSI chips. Okay? So this is much, much more important. And it's important because you have to put into this framework the different physics and the logics of the physics that come about from the different domains of engineering. And that's not easy. So this is what we did. This is the slide I like. It captures many of the things I will talk about. So if you want to design a system, what do you do? And how do you go about it in an organized way? Because the only way you can do these things for things of the complexity we're talking about is to do that in a very organized way. So first you have to sit down and write your notes. What is the system you want to do? I want to build a car, I want to be comfortable, I want to do a supply chain management system, I want to do a healthcare thing in the hospital, and it has to do certain things. Right? So you write them down in English or Chinese or whatever is your language. Right? And then you try creating something which we call, it's called use cases. Right? So you have basically described scenario of the use of the system, and while you do that, you're trying to create descriptions of the behavior of the system, and descriptions of the structure of the system. This is trying to answer the question, what the system does. And that means typically, if you have components of the system, you have to go down and describe what every component does. Right? So the wheel of the car is going to stop it, or when I try, it's going to start turning, it's going to do things like that when I turn and so on. So you write this, and this becomes essentially time sequences of events for these various components and subcomponents. You collect all those together, and that's the behavior. And many of these things dynamically can be described by differential equations, automata, or all of the above, or it's just a program. The structure is different. It tries to answer the question what the system consists of. Okay, so you have a car, and you want to have a comfortable car. And the car is going to have wheels, it's going to have chassis, it's going to have braking. So when you say I want to have a comfortable car, which part of the car is going to do that? Right? It's not the roof, right? But definitely the wheels, the brakes, right? The chassis and many other things, not one component alone. All right, and then the difficult part is to try to address what part of the behavior is going to be done in what part of the structure. Okay. And this is the mapping of behavior to structure, because not everything is going to be in every piece of the behavior. And at that point, you're ready to start taking your language or common language description of the requirements of the system and turn them into mathematics representations of these requirements, which typically appear as either inequalities, including logical and continuous variables, or metrics. And then you have to allocate those requirements to the pieces of the behavior, the pieces of the structure. Example, I want a car that can brake from 60 miles an hour to 0 to 200 yards. That's a specification, which I can write down in terms of mathematics, because of the kinematics of the car at the time. Or I want a shock absorber in the car that has certain elasticity constant, so I can have a certain absorption of shocks as I go through bumps. So this is in this process, but you have to keep it A, orderly, B, as you try and divide the behavior into pieces and the structure into pieces, you will find that you create derivative requirements. Right? So I say, I want a density carrier unit that is efficient. What does it mean about the equipment I have in the density carrier unit? What does it mean about the cost? I will generate new requirements. Right? I want the faults of the different devices I have in the hospital not to overlap, or I want to understand it, and things like that. And one of the most difficult issues here is to keep trace of the requirements you started and the requirements of the components in a mathematically consistent way. Why? Because as you go down through this, because I don't know if you see, but there are arrows over here. So these are all iterative processes. You want to be able to understand when you stop somewhere because you find something that's not feasible, where you stop, where you go back to start again. You cannot do that on top of your head anymore. You cannot do that if you don't keep traces of these requirements and derivative requirements in a very consistent way. Once you do all that, at that point, I claim you have an architectural system because you can tell me which behavior piece interacts with which behavior piece and on what structure it actually going to get executed. And that's what you would mean by architecture. Okay, so I have a building, I have doors, windows, and I have air conditioning. So, and I have insulation on the walls. So I can tell what part of the difference in temperature that I'm trying to create and I'm controlling the HVAC is going to be done by the walls, which one is going to be by the windows, which is going to be by the orifices I have in the roof. Things like that. At this point, you're ready to do trade-off analysis. The trade-off analysis we do by optimization. So optimization here is used as a tool to do trade-off analysis. And I'll show you a very complicated one if I have enough time today. Why? Because what you have, after you finish this part, you have written down a nice block diagram of the behavior, a nice block diagram of the structure, a mapping between the two, and these are annotated by requirements in terms of inequalities, which are constraints, or metrics. But the key to remember is that many of the systems today, they have logical variables and numerical variables because of the computers and also because of the logic of the physics. So at this point, you have a gigantic multi-criteria problem to satisfy. And we use optimization here not because we're trying to find an optimal problem, but because we're trying to understand trade-offs. Okay, and the two tools here are either multi-criteria optimization problems like industrial strength software like Cplex, or constraint-based reasoning software like the solver of Pilot. All of these things now belong to IBM. Okay, IBM saw the value of having software for this kind of designs, and they have collected a lot of things from Rhapsody and Russian and all, and some of these languages that for system modeling languages and so on and so forth, down to things of this nature. There are some other things you see here. All this stuff, by the way, are software. This is like for the later part. So once you do that, you do trade-off analysis, you may find that what you did here, it doesn't work. So that is going to force you to rearrange things, which means either you're going to join some boxes together or you split them. And you keep doing this until you find something that's feasible. And the last piece is you have to give me a testing and validation. Right? That is a procedure by which if I go buy what you did, I have to be able to test it, like you would test a chip. Or I have to check whether the specifications that you wrote here in English or in Chinese, they're actually satisfied by what you currently design. Now, the key point is that all this has to happen before you create this group, all by computer. That's the value. Because if you don't do that, you have a chance of failure of 70% according to industry standards. Now, can this be done? Yes. I've said it's a beautiful article we give to our students, even the graduates. In 1999, we described how this process was done for the airplane that most of you have flown already, the 777. Okay. Now, this is fine, but then what they did in 777 was expensive in terms of people and computers. So now everybody that builds a system, from the iPhones that you all have, to the iPads, to hospitals, everything, want to do systems engineering. And it has to be done in an economical way, and it has to save time and effort. Okay, so that's in a one slide what model-based system engineering is about. And what model means is that I have to have models for the behaviors, models for the structure, model for the physics of the structure, model for the optimization, everybody's model. Why is this new? How was system engineering was done before? By what was called paper-based system engineering, right? And we have even actually very famous companies come here, even as recently as 6 or 8 years ago, and we asked them, how do you do system engineering? We go to a room, we have a meeting, and we give notes, and so on. Good luck. Because you have to capture whatever, because these are things that they do that. And you have to capture the information in the appropriate infrastructures that you have to describe what. So that's why this is exciting, and that's why in the last 5 years this has become a very hot topic, the model-based system engineering. Now, behind all these things that is easy to say and difficult to do is you have mathematics and things for systems that they are not easy, right? Going from one modeling to automata to languages, trade-off analysis, optimization, validation, and so on and so forth. But the dream is, and this is going to happen, it's happening already, but it's going to be completed for several areas within the next, let's say, 10 to 20 years, is to actually have this completely automated with tools that you can all use, right? Now, some of that already exists. We have it in the lab and the courses we do. So I will go through with the most recent development. But the most recent development is that what is the central piece to it? How do I capture the system so I can think about my other tools? And what people have struggled with is to have a way to describe the system architecture in a way, that it can allow you to write block diagrams for behavior and structure in such a way so the block diagrams can be annotated by design variables, methods, and so on and so forth, and in such a way so that your favorite simulation modeling tools like MATLAB, Modelica, COMSOL, whatever you use in your area, can be linked to that. And initially they tried to do that with UML, which is a language that came from software. And it was too complex, too rich for general concept systems. And then IEEE and many other organizations came up with a code, and this new language was called SysML has been created. Okay, so what is SysML? SysML is trying to describe these characteristics of the system we went around by modeling the components, the behaviors, the mapping between behavior and structure. We see diagrams like this. So it is a block diagram language, not a programming language. But it allows you to annotate the blocks with parameters and requirements. Okay? And this allows you to model across different domains by linking them to the more detailed tools that you have in the specific area you work with. And it is a tool for managing the complexity. I repeat, it's not a programming language, it's a representation language. Right? Or if you want to think more simply, it's a block diagram language. Okay, so here's an example of the 4 pillars, as they are called, of this SysML. So you have to write a functional behavior model. So if you have a car, this describes on the car that I start, I sit, I accelerate, I brake. And then if I go down to specific pieces of the car, I have to write similar sequence of events for the pieces of the car. And then I have to describe the performance model, the structural model, in terms of the engine, and then other engineering analysis models. So you will hear people, they try to teach you this stuff, to say that once I have a SysML model of the architecture, and you will see examples of this, I can now interact with this with more detailed languages that I use in my own modeling for simulation, chemistry, physics, kinematics, mechanics, and so forth. And MATLAB, that MATLAB, and other things. Right? But these are analysis tools that they interact with the architecture model and they leave something behind in a way that different discipline engineers can understand. This is what the claim is made here by this technique. And as we say, the 4 pillars are the structure, the behavior, right? So here you see you have a library of electronic processor, and this is from a braking system for a car. You have an anti-lock controller. Everything you see here, even these dots and these dots have a semantic. They mean it's a piece of, or it contains a two pair. Okay, so this is a representation language that has semantics in terms of how the pieces of the structure connect to each other. Right? What is a part of how the components are. And then you can have here a traction detector and a brake modulator. These are again pieces of the part. And you can imagine writing this down in a very complicated block diagram. Then you go on this side, and this is what most of you do, and most of us do, and you forget this piece. These are dynamics. And as I said, you go through these scenarios and you write down what is that, right? So you detect the track loss. So you set the signal, then something else gets activated. So how do they look like? They look like lines of events, and lines like this that they show that how components communicate with each other. All these semantics are within here, and you can show interactions between components and so on. Right? And then you can actually show feedback loops in this scheme and many things. Right? So this can get pretty hairy. We're talking about systems that they may have 1,000 components or more. Right? But there's a way to look at this hierarchically at different levels of resolution. Now, the new things that came from with SysML is requirements. So I can actually go here and write vehicle system specification, stopping distance, right? As I was telling you, I want to stop from 60 miles per hour within 150 feet on zero on a clean surface. And you can write them in English, and then you can translate it into math. Or I can do anti-lock performance, right? So this is what I mean by annotating the block diagrams here with this kind of descriptions. And you can do them first in English or your other language, and then you can translate those, some of them, to mathematics or rules. And we want systems that they can automatically understand that and take them into account when we do trade-off analysis. Right? And there are tools like this that we have in the class, and we teach them. And then in parametrics, you want to say, all right, let's take this braking distance. I have several parameters, the speed by which I characterize it and how far I can go. So when you want to change the specification, what are you going to change? You can say, I want to go from 60 miles per hour to zero, not in 150 feet or 150 yards, but 100. And one of the things that we don't know yet how to do is, if we change this requirement, what is the impact of this to the various things you already done, right? So this. All right, so the way this process works is you start with the requirement repository, you create an architecture model using SysML, and then you start analyzing pieces of this. And if you go down the hierarchy by something like MATLAB, there's a controller box here. And then you leave something behind. Or you can go and use hardware models or software models and you leave something behind. The leaving something behind is extremely important because I work, let's say, with Professor Walt, who is a business, okay? And or with somebody else who is in microelectronics, right? We don't understand each other's language completely. We have partial coverage. So we want to be able to leave things behind that if he goes through it, we call, or she goes through her own lens, her own analysis, we'll be able to pick up the things that left and do the part of the system that she or he cares about. This is a challenge. Right? And I'm not telling you we have the answer, but we start seeing, as we say, the light at the end of the tunnel. And here you can do verification models. This is very important. I want to be able to have automatic things which involve programs that if I put it in and test my design, either by simulation or by automatically, I can actually verify. The goal is to have as much as possible automatic verification validation. Why? What's the most expensive part of designing systems is actually the validation of the verification. I don't know how many of you have been involved in testing software. I had students that they quit their jobs because after designing the software, they were spending hours in testing for bugs. And that is easy compared to what we're trying to do here. Because bugs are faults in software. Here we're talking about failures of specifications, which are bugs for physics, chemistry, and so on. So that's another sort of dream side. Yeah.
How do you avoid, in constructing the system architecture model, kind of putting in artifacts that are constraining the problem too much? I mean, you might imagine you have a...
Beautiful question. Here is the answer. You must constrain it to simplify. Sounds crazy? To create from a system a component, I have to constrain it to go to a subset. But because I go to a subset, now I have the flexibility of resynthesizing, reconnecting the components so I can simplify. All right? So they call this, constrain to simplify. So it doesn't matter if you constrain, because remember, there's no optimal design here. All we would like to do is try to find a way to introduce the constraint that I mentioned in such a way so I can go to a feasible design. The feasible means when I test, at the end, it passes my specification. Answer your question? And you will see through that. Now here's an example for many of you working in robotics, right? This is an example, Germany, and also Georgia Tech worked on a similar problem, and we are working on it here, trying to apply these techniques to design robotic arms in a way that is systematically the same, but we can do it for Sarah is not here. For Sarah Becker-Breyer's microcontrollers, or what Professor Bruno Martins and you are working and Professor Smela, where you have actually micro robots with the specificity of the materials and so on and so forth, all the way to the arms that Professor Aiken does in the aerospace department for NASA. Because what do the arms do, right? They have to move, they have to see it, and then they have to grab things sometimes or do other things, right? So here is an example where they developed a robotic arm for industry applications, where they link systematic description of that with things like Modelica modeling. Why Modelica? Because Modelica is a software that allows you to model multiple physics, right? When I do robotic arms, it's not just all mechanical. Remember, one of the problems, let's say you want to build a gripper. How do you build the thing? What is the haptic interface? Is it going to be a little bubble that has a haptic, or is it going to be some other material? You have to select that. So that's a part of the design. So design here is not just set the parameters, but maybe even the technology you choose and get characteristics. The beauty of doing it this way is once you do this diagram that I described, you can link to MATLAB and Modelica, and then if you want to build a controller, you can use your MATLAB tool. You push the button, all this is automatically generated, and you can actually see on the screen how things behave, which is part of testing and validation. Okay? We're trying to apply similar ideas to collaborative robotics. Now, this is another dream slide. Okay? This doesn't exist. The theory and the software to do that doesn't exist. This is more of a wish we want to do. So this is about the car. I don't know how it's going to come out. But here, you see it says minimum turn ratios 24 feet, dry pavement braking distance 60 miles per hour to 110 feet. These are all specifications. And what it's supposed to show you is that I want to change now this from 60 miles per hour to 110 feet to 80 feet. And the question is, can you give me a tool that allows me to understand what do I have to change to satisfy this requirement? And there's a point where I bring it here. See, here you have many of the things that go into the engine, and shows you different constraints that they are related to what we call before derivative requirements in different parts of the system. First, you see that many systems now have geometry. So challenge number one in many of the systems is we don't have a consistent way to describe geometry in orbit. In other words, geometrically annotated systems. This is important for aerospace, that's where it started, but it's important in robotics, it's important in hospitals, and so on and so forth. It's not just block diagrams. They are things that they are somewhere in space and time. Okay? And then you have engines and batteries and so on and so forth. So you go now to the schematics, to the diagrams. Right? And if this is properly done, again I said this is a dream slide, we don't have it. There are controls and so on and so forth. This is going to tell you what impacts what, and then you will go to these things and you change it. So we don't have good tools for understanding the impact of the change of some specifications to what pieces I have to change. This is an instance of what? Of traceability. Because I'm changing some requirement, and I want to trace back in my relationship between the requirements from the systems, the components, and so on and so forth, to find out what do I have to change. Satisfy the requirement is simple. I want to go, instead of 200 feet, to 100 feet for brake. What do I have to change? Do I have to change the battery? Do I have to change the brakes? Do I have to change the computer? What do I have to change? Right? But I don't want to go through this and have a meeting to do it. It take 3 days. I want to be able to do it with the software, and only the appropriate people to think very quickly. That's the challenge. So that's the fiction. Now I'm going to
Question.
Yeah.
You can think of, you ask one question, you can think of 1,000 questions like that you might even ask, but it seems to me there's a question of to what degree do you want to build so many complicated models that you can answer all those questions? I mean, you know what I mean? In other words,
Good question.
what's the trade-off between all the models you have to integrate and build and the cost?
Okay, so remember that the way this proceeds is in layers. So in the beginning, we do what's called a gross system model, where we don't break things into very small pieces. And the process I described in this diagram, so we go back a little bit, is another dimension that I didn't have space to put. If you go to my favorite diagram here with these, right? Back here, this is happens in layers. Right? So I may have very big boxes in the beginning where things are simple. And as a matter of fact, you have to repeat this process with all these layers. And once you're happy with the layers, you go down and you break them more and more and more. That's how you manage the issues you bring up. Because, in other words, the design cannot be flat. It has to be hierarchical. If you go flat, forget it. It doesn't help you. Also, you have to be careful when you create new components because you divide and conquer. Well, if you divide too much, the connectivity, as we say, between the components is going to kill you because it's an n cube problem. It's not an n square problem. Okay. So definitely you have to do the layers. These are called in practice design level A, design level B, design level C. And then once you understand pieces, you can take them and that becomes a system and you can give the team to do the system engineering for that. And then they come back. Okay. That's because if we don't do it carefully, we're going to get into the problem that Professor Ball mentioned. Okay. You're going to have a more complex problem than you had in the beginning. And then instead of actually solving problems, they're going to be handling, you're going to be playing with problems that your software has. And you don't want to do that.
But I'm saying, even if you design it and divide it into layers, there's a problem of deciding how much to invest in your systems engineering. Right? I mean,
Yeah.
you know what I mean?
Right. Right? So what's the answer? Standards. There's a big effort with the various communities, the IEEE, main organizations, to create standardized tools for which experts in software, they create these tools, and they are getting now more spread used by various companies, because definitely not even large companies can any longer afford to do this by themselves. So they want to be able to buy software and put them in integrated. So there is an industry being created, in which IBM is the leader currently, to create these integrated systems, okay? Design software where people can do them in a very interactive and easy way and avoiding the problems you mentioned. If I had to do it by scratch, today nobody would do that. It used to be when we started the institute, we go to places like IBM and Lockheed Martin, and they say, I don't want to talk to you about system engineering because this is my age of differentiation and I don't want to share with anybody else. But then they realize this is too complex. Okay, so now there are many, there's the INCOSI, this is the International Council for System Engineering, and now IEEE and the Systems Council, and the fact, and the SME and the other engineering societies, the fact that this large society get involved is very important because their membership is much, much larger than the small group of, because, I mean, two of the members, because it has 7,000, 10,000 people, IEEE has 400,000 members. Okay.
How do you capture expertise, domain expertise? Because if I take your car example, just ask me, I can tell you what you have to do.
Good. I mean,
I'm not even an expert.
Okay, when you write the models for the behavior and the structure, and you map the constraints to the behavior and the structure, that's where the experts come in. So, for instance, our director, President, okay, and myself and Mark Weston, okay, we're trying to create things like that for MEMS. I don't know much about MEMS. He doesn't know much about these things, right? So we sit together and say, all right, if I'm going to create a braking system, or a, what do you call this thing that you use with sharp for some time? I don't even know what it was like, okay? So how do you specify this thing? I can tell you what is the geometry and so on and so forth, but then he has to come in and say, you cannot do this in MEMS because this is a non-allowed design. There are rules. And that is captured then, right?
So would that impact the constraints of Campbell?
Yeah. So these are constraints, and think of, I use the words constraints and rules invariable on this thing. So you can write down, I can do that in plain language, and I can translate that to a rule.
What I'm asking is a little different, right? Because if you go to your car situation, I mean, everybody who cares about cars knows that the answer to your question is make the tires bigger, make the brake force larger.
So let me ask you, since you are the expert on cars, right? When you brake in the modern cars, how many components get involved?
How many components can
Of the car. How many pieces of the car actually get involved today in modern cars in the braking function?
That's a harder question.
Let me make the question harder and not tough on you. Does your seat get involved? Where you're sitting? No, that's how the matter. Because in the old function cars, okay, you push the brake pedal, and things will go on the wheel, the brake, and everybody understands that. Now I have to tell you that they got a problem, and then do mechanics. It was all electronics. The fact that you were pushing the brake was only because the humans will not accept the brake if it doesn't brake. It's all electronic. For the same reason, when we're working with wireless devices, none of those guys who had where they had an antenna here. This was not an antenna. Because humans would not use those days the wireless phone if you have an antenna. The antenna was back here.
That's missing my point, though, right?
What's the point?
I mean, the model can the model is much more complicated than the problem really is. That you need someone to tell you what to do.
No. Then if you do what you just described, then you have not done the system engineering model at the appropriate level of complexity. Right?
I mean, his question relates to my question. I think what Bill said, he said, I want to improve the braking system. An expert will say, okay, make the tires thicker, do this and do that. They solve the problem in 5 minutes. And now to create a model that tells you how to make the seats bigger and the tires bigger, that could take a lot of research, et cetera, to create such a model that would tell you that.
Except for what
whereas
you-
an expert might be able to tell you in 5 minutes. And the question is, when do you want to invest in all those models to do these things? And when?
Okay, that's a good question, but there are several counterexamples to what you just said. Okay. Because of the fact that we have now network embedded systems, right? Even the simple question of how to solve the braking system, it doesn't have just an expert answer. Why? Because by reprogramming the functions, I can involve more than one piece. I can involve the wheel, the chassis, and several other pieces in braking. And nobody knows on top of their head, right? Because they're now involved 3 different expertises, including electronics. Which one is the cheaper and best performance? And for instance, now people are putting measurement into the tires themselves. Now, but the answer to what you're really getting at is one word: reuse. Okay, so the idea is that people have already models of these things, and they're using them to build the system. Nobody in their proper state of mind is going to go and do this from scratch. So there are libraries of models, right? Some of them are becoming reasonably open because they are competitive. And then by tweaking them, you can take a lot of that from existing models, reuse them, and then do your work. And again, these are teams. The teams are they can be pretty large. But the fact is that without this thing, you cannot really go across domains and tackle it. Because it's not a single expertise question anymore. It's a multiple expertise question. So, but reuse is very important. And this is another word for modularity.
Reuse is a great idea, but you still,
Yeah.
see,
How can you imagine anything more complex than 0.777?
the impact, Boeing did just a very small fraction of the real design. Remember that they've been building aircraft for a gazillion years.
Yes, right.
And that they knew an awful lot about the airplane they were going to use. That was not, so they did certain things by computer that weren't done that way before, like a line of bolt holes.
But first of all,
But
Boeing
you
didn't.
didn't do a design from scratch. It's just ridiculous to say that that's what they did.
I just said that you cannot do a design from scratch, didn't I? That answered this question, okay?
Yeah.
But first of all, Boeing didn't do the system engineering because at that point they were not the best in the world. They got the Dassault and the sub company there, okay? And what did Dassault do, okay? Exactly modules, okay? Things like that.
And modules.
Nobody's gonna go and do a wing from start.
As you know, I think there are an awful lot of very good ideas here, but you do have to, but the point about the expertise is one you shouldn't overlook. It's certainly
You're
true.
not overlooking. Right? The point here is you don't go to the vertical. We all like to become expert engineers, right? What we forget is that if you go down first that way, and you build the little gadget that you're fascinated with, when you put it into the system, it doesn't work, then what? What do we do then?
No, I agree with that, but that's an analysis problem. It's not.
It's this is actually another word for it. It's called analysis, synthesis by analysis. Right? Let me give you an example. This is not going to work the way I wanted to work it, but I'll tell you. So, this is actually a problem in many of us work. Okay? So you want to have a way to design wireless network protocols so they can be adapted to different environments, indoor, outdoors, whether you have, Wi-Fi or whatever, and be able to have little gadgets that they are these nodes that they can connect to many wireless networks and eventually to the fixed network. Right? So if you look at wireless networks, they have the so-called layer-based protocols, right? I have protocols for doing network level, the routing. I have the media access control, which the policeman who tells me who gets to send the packet wirelessly. And then I have the physical layer, which tells me, what modulation and coding I do. And then you can say, well, that's enough, right? I mean, these are components, and they've been working for years, and what's the problem? Well, the problem is if you try to adapt this kind of protocols, which are huge in their own right, in particular the routing, to when I move in and out, okay, you cannot do it. Because they are very monolithic, and their performance is influenced by different pieces. So one piece of these protocols may do well in one environment, the other will do worse, and when you put them together, it's very difficult to improve it. So, And this started from applications in defense, but then it became commercial. So what's the issue? Break the components, break the physical, break the classical layer to pieces, appropriately designed pieces. And the only reason I put it here is not only it works, but we actually redesigned routing protocols that they were standards by these techniques, that they beat ad hoc IRCs. IRC is the request for comments that you put into the internet. So, and all the keywords that we discussed already are here. Right? But there is a big challenge. If I break the protocol, let's say the routing layer to pieces, and I will show you how do you put it back together in such a way so you can actually predictably or by proof say what's the property of the overall system based on the properties of the components. So this is a very good example where we started 5 years ago through the CDA with identification networking. And again, people, you know, they knew the problem, but they didn't believe that this was going to work. They brought up all the questions you raised. Okay? And the way it works is you build in a hierarchical way, every one of them has layers, 3 models. Executable models, think of them as programs that you can put into your nodes and they work. These are formal models like automata and others that you use for timing analysis and correctness and deadlock freedness and so on and so forth, and performance models. The arrows here is technically what is called bias simulations, right? Bias simulations, right? And we'll be able to have certain, not exact modeling correspondence because there may be reduction, because if this is actual code, it's going to be a lot more complex than what I have over here. This part, we understand fairly well. Professor Sifakis is coming May 5th, May 5. He's 30 award winner for model checking. He's going to talk about this part in the distinct lecture we have. The difficulty is to connect performance models. So if I want to understand delay, throughput, and so on and so forth with this stuff, how do I do it? This is still not complete. So we did improve there. These are reasons why you want to have top components in network protocol design and so on. And this is a diagram that shows you I have routing, scheduling, media access control, and physical layer, and how they interact. Right? So I have traffic demand, mobility patterns, and so on and so forth. And we parameterize the pieces of these protocols. We used multi-criteria optimization to improve them because many of these things were so complex that we could not write a nice model down in terms of automata. We actually, the best model we could do is write a program, which is a model, by the way. And we had to do actually things like automatic differentiation, compute sensitivity, and so on and so forth. There are many papers we wrote on this, but I don't want to talk about this. I want to go to a very concrete problem. We looked at the protocol which is called OLSR, which is very common and the favorite for many users for routing in mobile app networks. And we broke the routing component to 4 pieces. Nothing works in wireless networks unless you find your neighbor. Who is around? Why? Because then you can only hear people who set distance, right? You cannot hear the message. Then we used something that's called the selective topology information to disseminate. How do I go from the local neighborhood description, what information I transmit to others, so the totality of the users have a pretty good information topology? If I don't have pretty good information topology, how am I going to use it? Then you have to describe how to disseminate. So you want to broadcast to everybody, and you get a broadcast home. What's the method? And then finally route selection. So 1 layer component, we made 4. Now, people try to go below that, making more components, but then we go to the problem we discussed before and so forth. You have too many components and things don't work very well. And then there are my components and so on. So let's go back to that. This is how these connect. So this is the neighborhood discovery component, the selector of topology information disseminated, and topology dissemination. And we looked at the metrics we had in each of them. So you want to have minimum delay for the packet to go through. What does this do? Is it because you take too much time to find a neighbor? Is it because it takes too much time for the local information to go to the global? How much of the optimality that you want in the path is preserved when you do that? Can you answer anything? It's a very, very hard problem. But, we did a very extent. This is what part of that was the thesis of Kiran and several other students. So, let me skip that. This is the most difficult components where we have the most advanced, the stable path topology control. And let me give you a simple example. This is the neighborhood discovery component. So basically the way it works is you send a hello message and you get an answer. So you have 2 questions to answer. How many times I have to wait? How many times I have to resend the hello message before I say if I don't get an answer, I don't get a neighborhood? for a particular person, and how many times, you have to hear it before you say, yes, you are a neighbor. So there are two parameters. Okay? The number of states you have here and the number of states you have here. So there was a selection, and there are Markov chains underneath them. It's simple. You can all do the math, but that's not the point. The point is that if you change the parameters of up and down from the standard one to this one, you see these curves? Which one you will choose if you want to have an accurate description of who is your neighbor or not? Obviously this one. Because this is much more soft and you make more error. It doesn't take a rocket science to understand that. But this was fixed at that forever. And then we did this simple change and we got actually in actual simulations and tests much better throughput and delay for this protocol just by changing the neighborhood discovery component. And if I can go, and these are the graphs that they show you. If I go to the more complicated problem of this selection of topology, you tell me how much time, when you want me to stop, because 5 minutes? Okay. So let me show you that, and then we'll stop here. If you want, I can give you another lecture at some point, okay, for some of the other applications I have. The problem here was, how do I mathematize this problem of selection of topology information dissemination? How do I make it a problem that I can analyze? So this is all the stuff I get in the article about semi-rings and so on and so forth. See, the problem is, you want to have some local information, which is your neighbors. First question you have to answer is, what is the minimum amount of local information I need so I can actually do a selective of topology information disseminate that works? We know just the neighborhood information is not good. There are mathematical theories that tell you need second order information. But these are not constructed. So you cannot build them out. You know that they exist and what you know. So the traditional way was just basically you have the neighborhood discovering link state routing protocols, which is OLSI is one example of them. And then you disseminate this information, and then you can create broadcast storms because everybody starts sending this information around. You have a problem, so what they did is in OLSR there is a component, an algorithm is called NPR. You select the multi-relay random points, and these are like cluster cache, but they send the information to others, so you don't send it from everywhere. What we did was a lot more sophisticated. Okay, so basically we put this component in the middle here, and then we asked the following question here, right? So we went to mathematics, which I will not go through. But the key question was, if I have a subgraph of a graph, and I have a set of paths from 2 nodes, right, based on the full information of the graph, I want to be able to have a selection of topology disseminated components so that I can prove that at least one local optimal path is preserved when I construct the local optimal paths based on this reduced information. Otherwise, I haven't done it. And this is the problem to solve. And how it works is you take the local view, which is basically some, as you see here, second neighbor information. You don't need to send the resets. It's redundant. So I only get second order option because mathematically I need second order information. That's the local information. Then I define what is the so-called broadcast information that I send, which are some important nodes that they go from the periphery of my second order neighborhood outside. That's a small subset that I have we have a very concrete way of thinking. Then you look at the union of the local information, the broadcast information. You solve the so-called spot problem with this information, and you saw that under certain conditions, which are fairly generous, you actually preserve at least a local path between any 2 nodes. So what this connects to component-based networking, this is just how difficult sometimes the mathematics get in terms of understanding what are the appropriate parameterizations and solutions to one of the components that the performance of that one. So there's a lot here, but the interesting thing that got us very excited is that a group of people from Europe redesigned the OLSR protocol by this metric, which is fairly, it makes good addition, but it was all ad hoc and heuristics. And this is called the OLSR ETX. And they redesigned it by doing shortest path with this kind of metric. But there was no analysis, right? No proof or anything. Not only we analyzed it, not only we improved it, right? But we also found out why some of the problems they had there were there. And actually, the person who did that was the son of Francois Batelli, some of you know, right? Who was a famous person. And when I saw Francois in January of 2010 in England, and I said, we have something you're going to like. And he said, make sure you read the initial paper. It's not me, it's my son. And this was the RFC they wrote, and we were able to actually improve it by using things like the metrics that multiple metrics and doing things that I described. And that was very exciting. And unfortunately, I'm running out of time. But what comes here in the mathematics that comes with many of the network problems is this so-called semirings. Okay? And semirings are basically binary. It's a set of things that you have. There's a set and then binary operations. And binary operations, which are analogs of addition and multiplication, they have distribution between them, but they don't have integers. The most famous of those is the matched class algebra that was used for manufacturing and communication networks. First with those that are populous starting from trust, and then with Kiran we extended this to multiply. And that's what comes to. And the problem comes about checking whether the semi-ring that comes from the application has a property that's called idempotency. If it is idempotent, this problem, there's a theorem that says if the semi-ring is idempotent, then you can actually do this local information and the broadcast information, and at least one local path is preserved. And there are zero papers on this. So I want to summarize it. And these are actual curves that show you the performance. Look at this. Okay? This is where they were, right? And this is where we got to do. This is the ad hoc design of the other side of the X, and this is out. So, another message, optimization and math and modeling works. It's just hard work, but it works. And this is not just soft stuff where people do by simulation and modeling. If you really want to do it, it will take some very, very good people to see that you use pieces. Now, people can reuse it. I don't know if you do this again. I experimented well.
I'll let you finish and then I'll argue with them.
But another application was, how do I do routing in again mobile wireless networks when I want to be able to automatically exclude nodes or links that they're not secure? So that involves two metrics: the delay here, say, and a trust metric. And then you have to do how to do trade-offs with the metrics. What's the simplest algorithm you know? Well, here's the simplest algorithm. I'll take one of the criteria, make it a constraint. And then I'll solve it. Here it works very beautifully because what it does, it says, this is the so-called epsilon games algorithm. You take one of the criteria, you make this less than say some epsilon, that forces you to drop some of the links, and then you do the routine of the reducer. That's another beautiful example of how you can do this thing that people were struggling. And now, if you don't believe the math, which I think you should believe math, you can go to the simulations, and indeed what happens is nodes that they are suspect don't get to send packets, and links that they are suspect don't get involved in paths. So this is two examples from wireless that we have done using this component-based networking, and this is again active research. Now, in terms of applications, one of the first industries that did this is cars. They came up with the AutoSAR, which is just essentially a system engineering model for 100-something computers that you have in the cars, and they go to 140. And unfortunately, most of it happened in Europe with BMW. There were some academics involved from here and there. Now there's another effort to do that for hybrid cars, electric. Actually, we have a project with this CPS with GM that they're trying to understand. And they use exactly the tools I mentioned, Professor Levine. The General Motors says that they're using SysML and these models and their simulation and all that stuff to try to understand how to design hybrid cars and so on and so forth. They're also working, I'm not trying to point, I'm just telling you this is points of information. We are working on the same thing with several companies on sensor networks. Right? FAA has made a big deal, that's Professor Ball's domain, of doing system engineering for that. Right? They haven't scratched the surface of this formal models for this. They're still doing it in marketing and very ad hoc. Security is another problem because just read the first word, the first sentence. I may have pieces of software and hardware that they are secure. When I put them together, there are theorems that tell you if you don't have third type conditions of trust, this doesn't work. The resulting system would be insecure. And so on. I can go on. Healthcare, with Jeffrey Harmony, Professor Harmony here, and several people, and people from School of Business, who did otherwise, and so on. We're trying to understand what this guy meant by saying we want more systems engineering. So what we're doing, we're taking the example of work we've done in system engineering with Professor Ball, Professor now, on process models and costs, and we're trying to do the same thing for internal so intensive care units. And system biology, some of you have heard me talk about the significance of understanding the side effects of drugs and doing lab on a chip by designing to understand the side effects and so on. So there are many, many areas. And let me just, to honor our director, I want to close with one slide if he allows me, with this area. We're trying to understand how this is the problem we are dealing with UTRC, United Technology Research Center. I never understood how complex the electrical and other networks are for aircraft. And they have built an extensive program. We collaborate with them in Berkeley and Caltech on understanding the so-called vehicle management system and how do you do system engineering for that in a systematic way. Right? This is the United Technology Research Center. What you may not know is that most of the vehicle management systems are not done by Boeing or the aircraft company. They have been parceled out to United Technologies and companies like that. And this is an expensive proposition. So much so that in order to actually test this, they built a special lab, very huge lab. But the work is done by modeling software and so on. So very, very many problems, immense. So from two very recent papers when we were starting interacting with Professor Gozzi, we found out this critical review of how bad the state of affairs in having integrated MEMS in IC components. You can read it. These are not my words, I can give you the paper. So what was the vision? Can I do from MEMS what I've done from the other side? Well, not so fast, but because these are not just three. They have several physics. That's what makes it different. So the other one from the industry was that need for extraction, so you do this. So what we're trying to do, there's a nice diagram somewhere here. We're trying to use these ideas. And you notice here I added some of the software he likes, right? So basically Modelica, CSV, ANSYS, and so on and so forth. This comes from modeling MEMS. And the dream we have is to actually do this diagram. This is SysML. These are different modeling domains that we have to transform from one to the other. To answer Professor Boyle's question and Professor Levin's question, we want to have a database of components, which are the modules. And then we need to actually do trade-off analysis. Theoretical challenge to all of you, right? But I don't want to tell you that. This is, as I said in the beginning, this is the beginning of this model-based system. The biggest challenge we have right now, we can do the modeling well, but we do not know how to integrate well this so-called modeling hub, or this modeling hub, with the trade-off analysis of the power of the log and simplex across scales. And we're working with the IBM research group at Hyper to do that in ourselves. Why this is difficult is because as you have different modeling techniques, let me close this thing up. Sorry. As you have these modeling techniques, imagine if I have here Modelica, all kinds of modeling tools, and I have hierarchies, how the heck I control, right, optimization and trade-off analysis across these hierarchies, right, and the consistency of the constraints? That's what we will go. Because not all these things are completely decomposable. So this is a very tough program. This is the one slide for component-based networking that I described. This is one slide. And where this came from? I'm trying to impress you by the density of the slide, but the impressive stuff is not that. The impressive stuff is that the Department of Defense just started a huge initiative on model-based system engineering. They call it Systems 2020. And it's going to be an R&D project for at least $100 million for the next 5 years to create many of these techniques for many of the defense department programs. So there is discussion of doing similar things with the agencies that are involved in non-defense systems, like FAA, Department of Commerce, and so on. Because everybody and his brother wants model-based system engineering, and you are. This will be posted so you can read it. But I want to finish, and these are the last two slides. We teach this stuff here, ladies and gentlemen. Come and take the course. And we teach them as master students, not even PhD students. So please come and take the course. And to even challenge even more, we now teach it to undergraduates. We had 15 undergraduates last semester, we had 40 this semester. If the powers to be in this university allow us to teach the course next semester, it will be 100. And this is hands-on, because you cannot, just to answer all of you, you don't learn this by me preaching you. You got to do it. And then either you see the value by doing it in what we call hands-on examples, or you can take, sometimes people take, this is too complex and I don't want to do it. I am an expert enough to do it on my own. And that's fine. Okay? The final arbiter is going to be the market, and who makes the products and who conquers the world with the products. It's not what I say, but what you say and so forth. Final sentence. This is the beginning. We can do the modeling in a complicated way. But marrying the modeling and describing the languages and so on and so forth, I had 2 slides of challenge program, each one of them very, very hard. It's the top priority, according to NSF, in the CPS program, to develop the systems methods. But it's also top priority in any other program that requires everything you can think of in energy. I didn't go through it. Energy efficiency, smart grid, and all that stuff. The biggest challenge is the systems problem. Healthcare is a systems problem. And some of these techniques actually have promised to help you.
Wonderful. Okay, we have time for a few questions. Mariana, can you
Professor Walter,
I have a question.
more than one.
So, I still have a concern, and it kind of relates to both Bill and my question. You do this communication thing, you know, you have all these dissertations or whatever, incredibly complicated model that applies in a very specific situation. Model-based systems engineering is going to work. You have to, this whole notion of having reusable models and general models, et cetera, et cetera. I mean, if every time you apply this, you have to do years of research to create all the models, I'm not sure it's a very, you know, useful, widely useful thing. What does it buy you if you have to invest huge amount of money?
But that's not what you do. Right? You're going the wrong direction. The idea here is that I do as much as I can the exact analysis of object-oriented models. Right? So I want to have generic black boxes. And then what you have to do is, A, you can design a small piece, create an instance of your own example, and borrow the rest from the previous developers and users. That's how it's going. I totally agree with you, but that's not the idea. The idea is to generalize the object-oriented idea and the component-based software to systems. Okay? Definitely it's not easy, right? But what's the alternative? You're going to simplify. Because if you don't have this, people will tell you, not me, I can bring you here other people with this. But if you really want to do design exploration, if you don't have this kind of tools, your design exploration is very limited to small variations of the design you already have, and that's not good enough. Now, definitely there are going to be very bright people that are going to find extremely good answers, just like that. But they have to be smarter than the iPhone team that did for Apple. They use Apple or the equivalent. They have to be smarter than the people designed the Boeing aircraft. They have to be smarter than the people at United Technologies that designed the new helicopter. I don't know if you went to the top of Sikorsky, but they were able to actually do a very fast helicopter, very light, by just one motor. Okay. So, sure. I mean, I'm not trying to tell you that this is God, and whatever you have is going to solve it. You have to be smart about how you use it.
But I guess it seems to me a really good kind of question is what are the simple yet powerful models that can be applied really, really broadly? That's, you know.
Because people realize that the models will be in different categories. They are things that are called ontologies, right? Which are classes of models in languages that they are for specific domain, right? So for medicine, there is an ontology that people can develop modeling languages and modules. For electromechanical systems, there will be another one. For chips, there will be another one. I don't think it's going to be, nobody says it's going to be one fits all, right?
No, I don't, not one fits all,
But I think MEMS could be actually a good
MEMS
example
can be a
to
good
address
example.
that because we deal with a vast variety of materials and technologies and processes. And if we can come up with a configuration that we can actually do this in a sort of a, having a generic model that could apply, then the challenges are to define those constraints and simplify them, and then use that model to apply
Or
that
define the
specific
interface.
application.
Give you another example, everybody understands it. Go to MATLAB. If you're a control person, they're already pre-designed controllers. It's called libraries. You can take them and use them. Right? But occasionally you find that in your application you need to do a new block.
Right.
Okay. That's the dream. That's the dream. You want a small percentage of new
Yeah,
blocks.
exactly. Right.
But then you want to have a way to take what exists, put your new block in, to be able to quickly analyze.
Yeah,
This is where this stands.
right.
Question.
May I have two set of questions for you? The first set of questions is,
Two sets of them. I have all night, I don't have a problem.
Comment is either the same.
okay, the first set of questions is regarding how far you think this bottom-up network design can go in terms of You may have a one.
First, it's not bottom up only.
It's not bottom up.
It's top down and bottom up.
Yes. Then I guess my question.
Very important.
Yes. I guess my question is, I'm assuming you will have a set of dependency graphs,
Yes.
and with some common modules, hopefully they can interchange.
With some hierarchy.
With some
If you
hierarchy.
don't have hierarchy,
Right.
you lose from the back.
Yeah. Then I guess the question is really, what about when you talk about different layers when they interact, can you put them into one dependency model, or they are more or less separate, and then human, us, we hook them together using some add-on plan?
Okay, the answer is very simple. I only talked about components here.
Right.
There are two pieces in the design: design of components and design of interfaces.
Right.
Right.
Exactly.
You have to address both, because the old picture of interfaces, which are basically ports and wires and the transfer wire, is wrong.
Right.
The interface themselves, because of the making of the components, even in software, has to be often smart enough to be able to translate.
Yes. Usually the interface part is the more difficult question.
But the real answer to the question is you have to do it hierarchically, top down, and then within each layer more details until you are satisfied, then go to the next layer.
And this effort is more or less more manual than automated.
No, it's automated.
You
If
need
you don't
to-
let me tell you, people in computer science proper
Right.
are now working on component-based networks.
Right.
Two famous examples. Nancy Linz, who is a Turing Award winner from MIT, with her students, are trying to develop mathematical models of components.
Right.
And Tim Griffin to the University of Cambridge, I knew him when he was in AT&T.
Right.
I went to a workshop there, and we met again after 50 years, and he is working
Right.
on doing exactly the same mathematical models for the traditional protocols of the internet, including things like that we all take for granted, the PGP. You know why? Because most of the protocols are essentially patchwork. So you cannot analyze patchwork by anything that is automatic or fast. You have to do it by simulation and in many, many hours, and it's unacceptable.
Right. I just want to make sure, clarify that this is a automated dissecting of the protocols, not based on manual dissecting and then automated process. So this is automatic
Okay,
analysis.
this is the question of the question.
Right.
There's nothing that creates something out of nothing, right?
Exactly.
So there has to be domain expertise
Right.
in thinking about what might be a reasonable set of components.
Okay, great.
And then the models come and so on.
Right. My next question is more or less a general question. I think you addressed a little bit in terms of ontology, but seems like in our work, the most difficult part is the interface. When you have this system architecture model and the integration framework, or in ontology in some subject domain, the really difficult part for us is how to really define the interface that is meaningful, that also can work with your current models. So we have some. This is not a math problem, rather. So.
I disagree, because to define the interface, you have to define the components and their specifications and what you want the interface to do. For instance, even in routing, if you are not careful and you break routing protocols in pieces, you try to resynthesize them, you can do stupid things.
Right.
You forget where, for instance, the information about the path is stored.
Right.
In some routing protocols. Let's say the one you understand here is,
Sure.
I cannot exactly mix proactive reactive
No,
very
no.
easily
Right.
because the memory of the paths and so on and so forth is stored in different areas.
Right.
So if I have requirements about delay, and I'm careless, and I do synthesis of protocols, then the resulting delay will be worse when I do this
Right.
approach. But the point is, right, if this is done right, when you do the testing and validation, it will tell you that. Versus doing it by the way you suggested, which is the way it's done today, by simulation and testing by hundreds of people, and getting the results. And then you tell people, this is look free, there's very nice behavior and so on and so forth. And then some smart guy one day does a simulation that he didn't do before, he comes and says, no, this is not look free, and he lays off. Which I have many examples of it, in routing protocols in particular.
What is your general insight in terms of composing and decomposing or decompositionality? How we can achieve this in a general perspective?
Whoever does any new theory in compositionality
Right.
has a very good chance on any of these topics
Right.
to get best dissertation awards from computer science or engineering.
Exactly. Yeah.
Example, that you will understand. Stability. I take stable system, let's say stable world.
Right.
I compose the resulting system, very likely will be unstable.
Exactly.
Except if I use a particular way to describe stability, which is related to shippability and passivity. And there are ways of that that you can actually, although it comes from physics, you can extend to discrete systems and automata and so forth. Then you have guarantee, albeit conservative, but you have guarantee that once I synthesize them and tell you how to synthesize them. Please come May 5th when Professor Spaki speaks, because he will tell you many examples of the top block about how do I compose computer systems and other things, and how do I design the interface so that the compositionality property is transferred.
Okay.
It's not easy,
Very hard for each of them.
but doable.
Let's thank our speaker one more time. Let's sit down for a few minutes, so if you have questions, just come over and ask me.